that it's recording. Yeah. All right, so we have the great pleasure of having Dusa McDuff today, and she will tell us about embedding ellipsoids into Hirzebruch surfaces. Thank you, Dusa.
Okay, so let's see now. There we are. So let's see. So I'm going to begin with a brief overview of the symplectic embedding problem, because I was told that you'd like a sort of introduction to what I'm doing, and then I'm talking about my recent work. And recently, I've been working in teams. I mean, I started in this women in math team involving Maria Bertozzi, Tara Holm, Emily Moore, Grace Mwakyoma, and Anna Rita Pires and Magill Weiler. So this was a team put together by the Association of Women in Math. And we met and we worked together. And after a lot of effort, we got some results. And then I've continued in a smaller collaboration with Nikki Magill and Magill and Weiler. And so we're looking at the standard symplectic structure on R4. I'm mostly talking about R4 because we have more tools there. And the basic question I'm looking at is, if you have open domains in R4, when can you embed one into the other symplectically? And of course, you can ask the question in any dimension, but we have more answers in dimension 4. So I'm going to concentrate in dimension 4. Now, the basic question is, what's special about symplectomorphisms? So in 2 dimensions, they preserve area, and we know that they have extra fixed points under certain situations. For example, Moses' twist theorem. But these results, when people looked at them, they don't extend to the volume preserving case. However, Arnold conjectured in the 1960s that they do extend to symplectic diffeomorphisms. And he made some very influential conjectures that people have been studying ever since, really. Now, related to this, Gromov was trying to understand the different kinds of structures that you can put on a manifold. For example, what about a volume form or a contact structure or a symplectic structure? What special things does a manifold need to have to possess these structures? And what kind of automorphisms do these structures have? So those are the questions he was looking at. And so he asked this one question. For example, if you have a compact symplectic manifold, then something that preserves the symplectic form certainly preserves volume. And he wanted to know what was the difference between the symplectic group and the volume preserving group. And obviously they're not the same, but could it possibly be true that every volume preserving diffeomorphism is a limit in the uniform C0 topology of a symplectomorphism? Or is there some other difference between them? So that was the kind of question he was looking at. And so he was not looking at trying to count fixed points. He was looking at a different kind of question. Suppose you take a ball in Euclidean space and you look at its image under a symplectomorphism. What can you say about it, sort of topologically? He's a topologist. And in 2 dimensions, there's nothing interesting you can say. This was studied by Moser. And if you have a closed disk in the plane, which is diffeomorphic to a region which has the same total area, then you can find an area preserving diffeomorphism from the disk to this region. So in other words, just the total area being the same is enough to give you something which preserves area pointwise, a diffeomorphism preserving area pointwise. But in higher dimensions, the question becomes very interesting. So Gromov looked at the situation where you take a ball, which is the simplest shape you could start with as your thing you're trying to map in. And then he looked at a cylinder, which is so the cylinder is, I'm writing in complex coordinates, but you restrict the first complex coordinate to lie in a disk of radius A, but otherwise everything is unconstrained. So the cylinder is constrained just in the first 2 dimensions and otherwise unconstrained. And you know this theorem, the non-squeezing theorem, it's very well known, that says this is a symplectic embedding of the ball into the cylinder only if the radius or the area of the ball is less than the area of the cylinder. In other words, there's some 2-dimensional invariant which is constraining that image. And of course, it doesn't constrain in the volume preserving situation, because if you are just trying to preserve volume, you can shrink in the first 2 coordinates, but expand in some of the other ones, and then squeeze a ball into the cylinder. because they both have infinite volume. So that makes a real difference. I mean, then this implies that certainly symplectic diffeomorphisms, if you close them in a C0 topology, you're not going to get all volume preserving diffeomorphisms. And so, you know, although you might think the non-squeezing theorem is just like a curiosity, it turns out to be a cornerstone of the modern theory. And Gromov and Ekeland-Hofer in the 1980s made a definition of what they call a symplectic capacity. So this is a measurement of there are lots of them now, but this one, particular one, you take the supremum of the size of a ball that embeds symplectically in U. And remember, A is the area of a two-dimensional section of this ball. And so this is a symplectic invariant. It's essentially two-dimensional. In other words, the cylinder has infinite volume, but it has finite capacity in this way, because this non-squeezing theorem says that the capacity of the cylinder ZA is just big A. And it's preserved by orientation-preserving diffeomorphisms. And conversely, orientation-preserving symplectomorphisms. But conversely, if you have an orientation diffeomorphism that preserves capacity of all open sets, then it preserves the symplectic form up to sign. So this property of this symplectic measurement you can make actually characterizes symplectomorphisms. And that was very, you know, that was sort of opened a lot of doors, because then you can say, okay, let's look at a homeomorphism that preserves this capacity, for example. What can you say about it? What you have a notion of a C0 symplectic structure. And there are lots of recent interesting developments there by Seyfadini, Humilier, Buchowski, Christopher Gardner. You may have heard of the solution of the simplicity conjecture about the area preserving disks on the area preserving diffeomorphisms of the disk. And that all came out of the study of C0 symplectic geometry and understanding of that. Now, there was a question, are there intermediate capacities? So Gromov's width is essentially two-dimensional, as I pointed out. And so an intermediate capacity, it would be a measurement C prime, which would have the following properties. It would be monotone. So if U embeds in V, then, well, C prime U is less than C prime V. And it would have the property that it would be infinite. There would be some intermediate M, dimension M, in between 1 and n, so that it would be infinite on something which is like B2IA times R to the complementary dimensions, where I is less than M. So this is confined in fewer than 2M dimensions. On the other hand, if it would be finite if you confined it in 2M dimensions. So this would say in dimension 4, there's a way of detecting things which are finite, where 4 dimensions are constrained, but you've got plenty of other ones that aren't. And so the question was, do these exist? And in 6 dimensions, this would be infinite on a 2-dimensional ball times R4, but finite on a 4-dimensional ball times R2. And this was shown, it was shown that this couldn't exist by Guth constructing a very clever symplectic embedding. And after improvements by Hein Kerman and Pellet-Lau-Rougenot, they found a symplectic embedding of a cylinder, so that's a 2-dimensional disk times, say, R4, embedded into a 4-dimensional ball, which has to be of size slightly bigger than 3, times the remaining dimensions, R2 in this case. And so this was a surprise that there was an embedding like this, and therefore no intermediate capacities. But this revived interest in the question about symplectic embeddings, because Guth had a very clever idea about how you do this embedding. And Hein has actually found better ways of using an old technique that Lalonde and I developed of folding, and using that to get very good embeddings of this kind. So anyway, that's what revived my interest in this question about symplectic embeddings, because it proved that it had this very nice consequence. And just to wrap up this discussion, I want to say there are lots of other symplectic measurements you can make. I gave you one capacity, which is given by the ball embedding thing, but there are many other ones to do with periodic orbits on the boundary and various things. so there are many other measurements you can make, and that we don't understand the relations between them. There's a conjecture by Viterbo that it's possible they all agree on convex subsets of our 2n, but that's not known. And even computing them for various things is very difficult. So there's lots of questions here. Now I want to talk about embedding 4-dimensional ellipsoids. So here we start off with an ellipsoid, which is EAB. So it's again complex coordinate Z1, Z2, where Z1 pi Z1 squared over A plus pi 2 Z2 squared over B is less than 1. So it means that one axis has got size area A and the other axis has area B. And the question is, when does one ellipsoid embed in another? And Guth actually, he constructed an embedding in 6 dimensions of one 6-dimensional ellipsoid into another and higher dimensions. So he was actually working with ellipsoids. But ellipsoids are a very nice shape. They have a beautiful, Hamiltonian flow on their boundary, and they're the sort of the most elementary, interesting thing you could look at. So Hofer was wondering, when does one ellipsoid embed in another? And he eventually made this conjecture that there's a purely numerical condition for when EAB embeds into ECD. And it's that NAB is less than or equal to NCD. So what does that mean? Well, NAB is a set of all non-negative integer combinations of A and B, arranged with multiplicities in increasing order. So that means if you start with, say, 1 and 4, then you have 0, and then you get 1, 2, 3, 4, and then you get 2 lots of 4, because you can either have 4 times 1 or you can have 4. And then you similarly get 2 lots of 5, because you can have 1 plus 4 and 5, 2 lots of 6, 2 lots of 7, 3 lots of 8, because now there are 3 ways of making 8, and so on. So you can write down what those numbers are. And similarly, for N2, you can write down what the numbers are. There are 2 ways of making 2, 3 ways of making 4, because you have twice the first A, you have the sum of A and B, and then you have twice B. And then there are 4 ways of making 6, and 5 ways of making 8, and so on. And if you look at this, the N22 is always bigger than or equal to N14, but point-wise, N1, it's always bigger than or equal to, and they are equals sometimes. They're equals at 8, they'll be equal at 10, and so on. But you can actually check very straightforwardly that in this case, N14 is less than or equal to N22. That's a simple arithmetic exercise. And then that means, Hofer said, well, in that case, there has to be an embedding. And so how do you construct that embedding? Well, I will tell you in a little bit in a minute, but this is his conjecture. And what are these numbers? Well, these numbers are the actions of the generators of a particular kind of homology theory called ECH, which is a 4-dimensional Floer type homology theory, which is related to gauge theory. So it only works in dimensions 4. And its generators are unions of closed orbits of the boundary Hamiltonian flow. So the thing is, if you look at this ellipsoid it's got, and take A over B irrational, then there are just 2 simple closed orbits. There's the one of size A and the one of size B. And if you want to look at unions of closed orbits, they have actions exactly Ka plus Lb. And there's this homology theory which says that each of these is a cycle. Each such union is a cycle. That's why you get these numbers. So Hutchins developed that theory. And so using his theory, he showed that if there is an embedding, these ECH generators are monotone, ECH series monotone. So NAB is less than or equal to NCD. So that follows from the theory of embedded contact homology. But I proved the other way around, that you can actually construct embeddings to prove this conjecture. And here's an illustration of what it means. So this is the ellipsoid into the ball embedding problem. So we define the capacity function, which is the smallest mu such that the embedding E1H embeds into the ball of size mu, right? That's what it is. And I calculated it with Felix Schlenk in 2012, and we got a really surprising answer. So obviously it's increasing, because if you make your ellipsoid, if X increases, the ellipsoid gets bigger. So it's an increasing function, and it's bounded below by volume, because the volume of E1x is a constant times x, and the volume of the ball is a constant times mu squared. And so that means x has to be bigger than the square root. So you have those things, but we thought it would just be some kind of increasing function. But it turns out to have this very striking behavior that for x up to the golden ratio to the power fourth, we have what's called an infinite staircase, so that it goes up in steps like this. You know, it goes up linearly on a line from the origin, and then it's horizontal, and then it goes up linearly again from the line, and then it's horizontal, and so on. And each of these corners are on the volume, so it hits the volume, and then there are infinitely many of those steps. And because it's the Fibonacci numbers, it converges to something to do with the golden ratio. And then there's some intermediate period. And then when you're big enough, it's always the case, these kind of problems in symplectic geometry, that everything disappears. If things are long and thin, there are no obstructions. So if x is sufficiently big, in this particular case, bigger than 17/6 squared, there are no more obstructions, and you just get the volume cut. And so, but you know, before tau to the fourth, we have a manifestation of rigidity in this sort of in this form. And this is what I said, that when x is sufficiently large, there's only the volume obstruction, and then you have this transitional region in between. And that function is fully calculated. It's very, very precise. But if you want to know what happens in higher dimensions, we don't know. There's, you know, just, you can say, well, what's the obvious analog? There's an obvious analog of Guth's conjecture, of Hofer's conjecture, and Guth's embedding shows that doesn't work. Because Guth, what he did was embed an ellipsoid which had a very big second coordinate. So it was constrained in the first coordinate, but the second and third coordinates were very big, arbitrarily big. But then he embedded it into something which was constrained in the first two coordinates. And that's why you know, there's no intermediate capacity there. And you can show that the existence of these beddings for all large S shows that the analog of Hofer's conjecture can't possibly be true. So nobody knows what the answer is in that case. So I'm going to concentrate on the four-dimensional case. Now, I want to explain a little bit. Oopsie. By the way, do you see, I've got all your faces in front of the top of the slide. Do you see that, or do you see, is it all right for you? I don't know.
I'm seeing very well.
You're seeing very well. Okay, I'll ignore that. Anyway, so I want to make, there's a connection with number theory here, as you can see, because we've got the Fibonacci numbers. So where do they come from? So they come from using toric geometry. And I notice some of you are toric geometers, so you'll like this bit. So we look at the moment map. So from Z, complex coordinate Z1, Z2, to, well, actually, it's sort of the square, you know, T1 and T2 are pi Z1, absolute value of Z1 squared, absolute value of Z2 squared. And then that takes an ellipsoid into a triangle, because this, you know, ellipsoid is quadratic, but this becomes linear in the T's. And so you get an ellipsoid, which is, it might look like this. This is T2, T3, 4. And the ball maps to what I think of as a standard triangle, which has got two sides of one. And then, you know, this map here is, you've collapsed out T2, but you could have chosen it to act differently. So it's you know, if you look at integral affine changes of basis of C2, like using this change of basis, then you see this triangle here going, this one is equivalent to this triangle here, this slanty one. So here I've got the triangle E1,3 cut up into three triangles E1,1, which are all equivalent. They're all images of balls. And so you can cut T1,3 into three standard triangles. And that implies that the E1,3, you can basically fully fill it with the open interiors of three disjoint balls. Because you can, there's a trick by Lisa Traynor saying you can, even though we haven't collapsed this side, you can still embed the interior of a ball into this open region here. So, you know, you can see, sometimes you can just draw these pictures and see you have embeddings, right? And if you look at a general triangle with integral sides, you can decompose it into standard triangles of different sizes. So here's one where I'm building T53, and I'm building it up from T33, T22, and 2 T11s. And how you can do that, if you think of triangles, you can take this triangle here, this one of size 3, you can add one of size 2 here, and then you see you've got a size 1 there. This is affine length 1, but this end is affine length 2. So I can add 2 standard triangles on there to add a copy of E12 there. Now, this looks rather complicated to understand, but if you see, you can build, instead of working with triangles, you can build rectangles from squares. So we can start off with this square, add another square the side there, and then add 2 squares there. And that's a decomposition of this rectangle of sides 3 and 5 into squares, very easy to understand. And you can get from this picture of squares to the picture of triangles by removing this point and then collapsing these outer edges to the boundary, and keep where these points are here, sort of keep where they are in an affine sense. So that means that this line here goes up to that line, and this line here is the image of that line, because this is going to move down there, and these points divide it into 2. So there's an analog between these 2 decompositions, just easier to understand on the square picture. And so that's an explanation of how these pictures are the same. And then the combinatorics of this decomposition to a triangles are actually related to continued fractions. And they govern what I call the integral weight expansion of a rational fraction. So here's a picture. Here's 25 over 9. And I take a rectangle 9, 25, and I just chop it up into as many 9 squares as I can, 2 of them. Then that leaves me 7 there, so I have a 7 square. That leaves me 2 up here, so I've got 3 2s, and then I have 2 1s. And so that gives you what I think of as the weight decomposition, which just it fills out the whole volume of this thing, and it gives you a string of numbers. But that string of numbers is related to the continued fraction decomposition, because if you take you've got 2 9s, and so you put a 2 there, you've got 1 7, that gives you a 1, you have 3 2s, that gives you a 3, and you have 2 1s, and that gives you a 2, and that's the continued fraction expansion of this thing. So if you expand, this is 2 plus 1 over 1 plus 1 over 3 plus 1 over a half, and you just expand and see that the same. So the point is that there's an analog between this decomposition of cutting a rectangle into squares, or equivalently cutting an ellipsoid into balls, with the continued fractions of the size of the ratios that you have. And that's the connection with number theory. Now, so to explain how it works for embedding ellipsoids, we suppose that P over Q, our rational number, has got a normalized weight expansion. So take what I was doing before and divide by Q. So that means that we start off, instead of starting off with Q, we start off with 1. We have 1s, and these are all rational numbers. And then then you haven't changed the volume. So the volume of this ellipsoid is the same as the volume of the corresponding squares. And you can prove, this is what I proved, that an ellipsoid E1P over Q embeds into a ball if and only if you can embed the disjoint union of the balls into the ball. And that was basically done by resolution of singularities and J-holomorphic curves, and I can't sort of go into that. Now, the point about this is that I'd worked with Polterovich in the 90s, and we know when you can embed balls, a bunch of balls into another ball, because that's connected to the problem of symplectic blowing up. So we know that you can embed these balls into the big ball if there's a symplectic form on the n-fold blow up of CP2 in a particular cohomology class. So the line has got size mu, so that's the size of the line in this projective space. And then each of the blown up, the exceptional divisors have got size W, the W's, these are the weights. And that's to do with the fact that blowing up in the symplectic world, you have a ball embedded in your manifold, you cut out the interior of the ball, and then you collapse the boundary to the Hopf surface. You collapse it to, and that gives you an exceptional divisor. And then, when are these? So then the question is, what is the symplectic cone of blowups of CP2? And that was again solved in the end by Li using gauge theory and stuff. And it happens only if A squared is bigger than 0. That's a volume constraint. And also the fact that your alpha has got to be positive on all the exceptional divisors on the blowup. And so the exceptional divisors, these are two-dimensional homology classes, which can be represented by symplectically embedded two spheres, which are rigid. They have self-intersection -1, so they sort of persist under deformations. And, if you know any complex geometry, exceptional divisors are things people work with. And so we now have a sort of geometric algebraic problem. What are the homology classes of the relevant exceptional divisors that actually are going to obstruct our embedding? Because there are not all of them. We want to our obstructions are, well, we want to embed this particular ellipsoid. So we're given a bunch of numbers here, and we want to know what's obstructing that embedding. So that's sort of the problem that Felix and I solved. And in the case when you're mapping into a ball, you calculate and you find out that the relevant exceptional divisors, the coefficients come from Fibonacci numbers. Now, what I've been doing now is looking at other targets. So instead of embedding into the ball, I've been embedding into the one-point blow-up of the ball. So you take CP2, which is, its toric model is a triangle, and you chop off a corner, which means you've embedded a ball and then you blow it up. And that gives you, if you know any toric geometry, this is the picture of CP2 blown up at one point, a Hirzebruch surface. And I'm thinking of a family of symplectic forms. So I fix the size of the line, and then I have this family of B, which tells me how much I've blown up. So it tells me how big is the acceptor, the -1 curve, the -1 section. So you can think of it also, if you're not familiar with toric geometry, as a S2 bundle over S2, which is non-trivial, and the fiber's got size 1 minus B, you've got a class which corresponds to the line of positive self-intersection of size 1, and then you've got this -1 class of size B. And so then we look at the embedding capacity function, which now depends on B. So we fix a B, and then we look at ellipsoids E1x, and we ask, how big do we have to inflate the target? So what's the minimum lambda you need in order to get an embedding? And that's called the embedding capacity function. That's what we were working at before. And so again, it's always bigger than the volume constraint, which you can easily work out. And it equals volume, again, when X is sufficiently large, just from general principles. And it's always, there are always these finite number or infinite number of obstructions. And so you can prove it's a maximum of the volume curve and a piecewise linear function. But this piecewise linear, there may be infinitely many obstructions. And we say that there's a staircase if there are infinitely many obstructions. So, typically there's just a finite number of awkward classes that give you obstructions, but sometimes there's infinitely many. So it's a sort of resonance phenomenon. When are there infinitely many? So that's what we were looking at, which B would give you an infinite staircase. And we started off by knowing that when B is a third, that's the monotone case, a Fano manifold. Then when B is a third, there is a staircase, that we know. And when B is 0, of course, you've got the ball, so there's a staircase. And the conjecture is still unsolved, that those are the only two rational values of B that admit a staircase. So we had Christopher Gardner and Tara Holm and Pires and Mandini had written a paper looking at this question in general. And so they were looking at basically four-dimensional almost toric manifolds. But they what their theorem is in the case of the Hirzebruch surface is that if it has a staircase, then the steps of the staircase have to converge to a particular point, which is called the accumulation point. And that point is a unique solution of this equation here. So this equation is an equation for x, and it's got its coefficient of x is, it's a coefficient of x depends on b. And so you have that there's one, since the product of the roots is 1, there's exactly one root bigger than 1, and that's the special value. And if there is a staircase, then the capacity function has to equal the volume at that case. So the obstructions actually have to converge to the volume. So that's where we were starting from. And in our particular case, what this function looks like is this. It's quite interesting. So b is our variable. So b starts off at 0 and goes to 1. And what we've written down is a parameterized curve where the time parameter, if you like, is b, and what we're the first coordinate is where the accumulation point is, and the second coordinate is where the volume is. So we start off here with b being 0, and this is the Fibonacci, the Fibonacci staircase, which converges to 2 to the 4th, which is less than 7. So that's its convergence thing. Then as b increases, the volume actually of the at that accumulation point decreases and takes a minimum at 6, and then it still, the accumulation point still decreases until you get to the minimum accumulation point, and this is the staircase at a third. So this is a very special point, the staircase at a third, and then it starts increasing again and goes up like that. So that's what this graph looks like. So the blue point has a Fibonacci stairs, and the green point is at a third with a staircase. And actually, there's a similar function for all rational toric domains. I'm just concentrating on this one example because we wanted to try and understand it. Now, so let me introduce some language. So if you're at a point where you see, if there is a staircase, we know that the capacity function at that special accumulation point is equal to the volume. So if you can calculate that at the accumulation, given a b, at that accumulation value, there is an obstruction, then there can't be a staircase. And we say that those b's are blocked. So there is a bunch of b's that are blocked. And what you can say, one basic question is, what's the structure of the set of b that are blocked? How many b's are blocked? And then we have a disjoint set stair, which are the set which have a staircase. And these are definitely disjoint sets. B the block by its very nature is open. And we know that stair contains these points 0 and a third. So one of our first results was that, well, actually, we've just achieved it in here. It's not our first result, it's one of our latest results, is that block is actually open and dense in 0, 1. So almost all points are blocked. And the other thing we found, which we sort of had inklings of in our first paper, and we've expanded our understanding of this, is that each interval in block is actually blocked by a particular class, and the staircase is at each end of those intervals. So there are ascending staircase at one end and descending staircases at the other end. And what we found is that each step of each of these staircases are given by obstructions, right? Because they're steps, they go above the accumulation curve. They're obstructions. They are themselves centers of blocked intervals. So, the blocked intervals are given by obstructions, but those obstructions organize themselves into staircases. And the organization into staircases is very interesting. So suppose we look at, instead of looking at the block B values, here the block is that these are the B values which can't have staircases. So let's look at the corresponding accumulation points. So these are Z values. And so let's look at this set. So these are the z values which are blocked for b's bigger than a third, because I told you b sort of divides, b less than a third and b bigger than a third are sort of separate regimes. And so the accumulation points here live in this interval, in between 3 plus 2 root 2, which is the accumulation point of the third staircase in infinity. And if we look at these intervals of length 2, so they go between 6 and 8 and 8 and 10 and 10 and 12 and so on, and we look at what the blocked intervals look like inside there. Well, they look like the complement of the middle third Cantor set. So they have interesting sort of interwoven structure in each of these intervals. So you have, in each interval, you have this family sort of like the complement of a middle third Cantor set, and that just replicated for each end bigger than a third. And then, you know, what else happens? This is for to things bigger than 6. Well, for things less than 6, there are symmetries which come from properties of this Diophantine equations that describe the rest of the image of blocks. So once you've understood what the staircases are when accumulate bigger than 6, you've got all the staircases, because we've got these symmetries. There's a shift and a reflection, and they give us all symmetries. All the staircases. And another thing we've proved is that all rational numbers, except for these very special ones, 6, 35 over 6, 204 over 35, are actually blocked. And so they're not accumulation points. So there's these special ones, which could possibly be accumulation points, though we think they're not. But then none of the other ones could be. But these are rational z values. And I suppose the more interesting question is what happens with rational b values, which we don't know. But actually, we have a proof, a rather complicated proof, that at 6, there is no staircase. But that proof is so complicated that none of us quite understand how to extend it to all the other ones. So we haven't figured that out yet. Anyway, so that's the picture of what we have, what we've proven. And I thought what I could do is try and explain a little bit what goes into the proof of this. This is the first kind of situation like this has been worked out, by the way, because Usher looked at the family of if you look at the trivial S2 bundle, then you've got it's just S2 times S2, and you vary its size by fixing one sphere to have size 1 and the other one to have size B. And he looked at that and he found infinitely many B values, where there were staircases, but he didn't know. This was before the paper which told us about this interesting fact about the accumulation point. So I'm sure that what we've done in this case can be extended to what he did, but he wasn't, he has, preliminary results, but it's not done yet. Anyway, so we have this conjecture that the stair consists only of these points 0 and a third and the endpoints of the intervals in block, but we haven't proven that. That's our conjecture. So now let me try and explain a little bit what's going on here. So here's a picture again of this parameterized curve. B goes to so we start with B equals 0, and this is the bit where B is less than a third. And the bit I'm interested in is this bit where B is bigger than a third. And what I've been telling you is what happens above 6. So in between 6 and 8, and then there's the next interval and so on. And here are some of what the staircases look like. So at 6, there's a class which blocks there with a center at that class, and it blocks a big thing. It blocks from 5.86 to 7.17 roughly. So a little bit below 6, but above 7. And there's another obstruction centered at 8, which blocks from a little bit above this point, a little bit below 8, to a little bit above 9. And there are similar ones for 10 and 12 and so on. So you have these big, what we call blocking classes. And then we have a sort of, at 7, 4. So this is 7 plus a quarter, right? Because we use continued fractions here. So that's 29 over 4. And then at 7, 5, 2. So that's 79 over 11. And 7, 3, 6 at 136, so 39 over 19. Those are 3 other blocking classes. So one, this one sort of lives in the middle here, and then this one is smaller. 752 is smaller than 714, and 736 is bigger than 4. And then here are what the staircase classes look like. I tell you, there's a staircase which has 8 as a step. It has 7, 4, it has 7, 5, 2, and then it has 7, 5, 1, 4, 7, 5, these ones, all these ones. And it converges. That's a staircase that converges to 7, 1, 7, the upper endpoint of 8, 6. And there's another one on the other side. So just to show you some of the numerics, what it looks like. Now, oh, I've gone backwards. I meant to go forward. Okay, so this is a picture that Morgan drew. She was the one who actually discovered a lot of these staircases using numerical methods. And so this is a picture of where our blocked intervals are. So we have this blocked interval at 6. We have a blocked interval at 8. This is absolutely not to scale. We have a blocked interval at 7, 4. And then in between that, we have a blocked interval at 7, 5, 2. And then in between those two, we have another one. In between those, we have another one. And similarly, in between this red one and this blue one, we have this green one. And then we have in between here, we have another one. So this is where the middle third Cantor set's coming in, because in between any two of these classes, we have another blocking class. So that's our middle third Cantor set. And what's all this about and the color coding? Well, there are staircases converging to each end of these things. So to the 6 and 8, which sort of live at the top level, the staircases are 2 periodic. So that means that when you look at the continued fractions, they repeat 2 digits. This one repeats 5 and 1, and this one repeats 7 and 3. So they're 2 periodic staircases. But when you look at the staircases converging here, they're 4 periodic staircases. And the one converging, the green ones, are 6 periodic. And the brown ones are 8 periodic. So this picture is in fact exactly the same as the picture that gives you the Fairy series for continued fractions. If you know about Fairy, you write all the fractions in between, say, 0 and 1 down as a over b, and you say b less than or equal to n. You write them all down and you get a picture exactly like this. So there's some really interesting things going on here. Now, that's sort of the first picture of what's going on. So I could tell you a little bit more about this, and I'm not quite sure how much time there is, but anyway. So let me say a little bit more about how do we prove this and what the relevant exceptional classes are. So a sectional class, we're working in the blowup of CP2, so we're looking at homology classes. So this is D times the line, that's the degree of our curve. We've got one special blowup, which is our blowup of size B. So that's got a coefficient M. And then we've got all the other blowups which correspond to the remnants of our ellipsoid, and they have size MI. And the best obstructions, which are the ones that give the outer corners of the staircase, have a very special form. So D and M, sort of whatever they are, but the MI, the coefficients here, are given by the weight expansion, the integral weight expansion of P over Q. So, if we're trying to, this is an obstruction centered at P over Q. And that somehow is just perfectly fitted to make it very difficult for an ellipsoid 1 P over Q to embed. It just gives you a very strong obstruction. And this is something we found an analog of this in the case of the ball. And it just, we didn't, in the case of the ball, this coefficient M is 0. All we're really doing is adding this new coefficient here. And these classes are called perfect classes because they give us these steps. And they always give an obstruction which is live at P over Q, which what that means is that you can see it. To say an obstruction is live means you can see it in the capacity function when B is about M over D. When B is exactly equal to M over D and then in some little region about it. So, these classes are always seen somehow in the obstruction function. And these classes actually correspond to exceptional divisors because they satisfy, the ones we're interested in satisfy these equations where C1 is 1, so that tells you that 3D is M plus P plus Q, and the self-intersection is -1, which tells you this numerical condition. and that E reduces correctly under Cremona moves. In other words, there's two purely numerical condition, and then there's a geometric condition which tells you that it's actually represented by this potential class. It's actually represented by an embedded sphere. So I should have put this actually before here, because the perfect classes are the ones which are actually exceptional classes. So they satisfy all these conditions. And of course, the numerical ones are easy to check, but the Cremona move one is hard to check because that's a sort of iterative checking. And classes that are defined as above from these tuples, that if they just satisfy the numerical conditions, but don't necessarily reduce properly, we call them quasi-perfect. I think that's blocked up. So then what we found is that every quasi-perfect class in this situation, D and M are actually determined by P and Q in a very interesting way. So if we look at this quantity T, which is the square root, this P squared minus 6PQ plus Q squared plus 8, then D is given by this particular formula in terms of P, Q, and T, and M is given by another related formula in terms of P, Q, and T, where epsilon is 1 if M over D is bigger than a third, and is minus 1 if M over T is less than a third. So in other words, our perfect condition, or the quasi-perfect condition, just gives us conditions on P over Q, but we can actually recast those numerical conditions I had before. These two numerical conditions, you can just rewrite them. I mean, you can get rid of M by substituting for M there, and then you rewrite this equation in terms of T, and you get this particular expression. And the wonderful thing about this expression is that it is invariant under our symmetries that we found. So it's very, the form of this is very closely related to the quadratic equation that gives you the accumulation curve. And so what we found is that the staircase at the limits at the end points of a block B interval JE, so that, our blocked intervals are given by these quasi-perfect classes. The variable, they're given by recursions, and the recursion variable of that class is the T coordinate of that JE, which was sort of an amazing thing. So that gives you a relation between the blocking classes and staircase. And as I said, this formula here is a key to understanding the symmetries. So they're induced by the shift. P over Q goes to 6P minus Q over P that fixes T. And then there's another reflection that I didn't mention. And so what we've actually proven now is that every quasi-perfect class, if you start with a quasi-perfect class that has center bigger than this, it's actually a blocking class. And we've got a better condition for something being perfect. Instead of having to check that that it reduces correctly under Cremona moves, which is impossible if you have very large coefficients. I mean, I don't know how you do that. You can check that the lower endpoint of the corresponding obstructed interval is actually unobstructed. So you get some information. What you're saying is that some information. To say it's unobstructed means that that at that particular value of B, we know that the capacity function is equal to the volume. So that gives us some information about the capacity function, and that's enough to say that E is live, it's seen by that capacity function. And so then we say, then we prove that then JE is actually a component. That's one of the components of block. So we get a perfect class. And we find that all components of block are given by these perfect blocking classes. So we found a way of describing block. And then we have an iterative construction, which I suppose I have just a minute to explain. So we started off with E6 and E8, which are our big blocking classes. These are what they look like in these coordinates, T, M, P, T. Then we had this middle class, E7, 4, and these classes are related by a lot of numerical conditions. They're not just completely arbitrary. And these numerical conditions have geometric meaning. And so what we can prove is that these two classes are the first two steps is in an ascending staircase with recursion parameter 5, which has blocking class E8, and E8 and E7, 4 are the first two classes in a descending sequence that goes to E6. And then, you know, these staircases, if you look at the third step of this one, so you go from E6 to E, then you go somewhere in between there. These three classes also are related in this very intricate way. So they satisfy all our conditions, so the whole thing replicates. So we have a pattern of these triples which generate staircases and which replicate. And so that gives us all our perfect classes. That's how we get all our perfect classes. And that's where we get this picture from. We get this picture from, you know, working out what the numerics are and then proving it replicates and finding this picture. And I think this is a good place to stop. Okay, so I think that's the end of it. And here are some, you know, these are some of the references. Our last paper about these recursive patterns is not quite finished yet. It'll be up soon. Okay, so I think this is a good place to stop. I'll stop sharing. And
thank you very much. Let's thank Dusa for the talk. And does anyone wants to post questions? Go ahead, unmute yourself and just ask.
Perhaps I could say that, you know, I've been looking at a very, very specific problem, which is, you might think it's not terribly interesting. You know, when does an ellipsoid embed into this Hirzebruch surface? Now, it seems amazing to me that this question has so much structure. But the other thing is that there are, you know, this kind of, the work that I did with Felix about embedding a ball into ellipsoids into a ball, we found some numerics which actually you see in other problems. It's related to the existence of Lagrangian submanifolds and things, and so the same combinatorics comes up in different situations. So I absolutely believe that this combinatorics that we're seeing here, you know, you see some of this kind of phenomena in tropical geometry and other kinds of areas. It's just that I've been concentrating in this one area, so I haven't looked at those other areas.
But
the other thing I should say is that actually we used almost toric vibrations here. So people interested in toric geometry, we needed to prove that our thing was unobstructed. And to prove that, one way of doing it is construct a fulfilling. So you just construct an embedding. And actually a very good way of doing that is by using almost toric vibrations. So we were using almost toric vibrations in our proof instead of using Cremona transforms. So that was a more geometric thing. I just didn't put it on the slide.
But is existence of staircases like a universal property of embeddings of ellipsoids?
Well, I mean, there's a conjecture that if you look at CP2 and you blow up, you know, if you look at CP2 blown up a certain number of times and look at things like its diffeomorphism group, it changes when you get to say 5 blowups. I mean, for the 3 blowups, you have a toric structure. 4 blowups, you don't have a toric structure, but you have an almost toric structure. 5 blowups, really things change, and so I think there's a conjecture that there wouldn't be any staircases in that case, and you might see remnants of this. I mean, certainly, you know, if you blow up twice, there'll be some remnants of this, and in fact, Nikki was working on it. I think there's very interesting extensions of this, but you know, we've just been focusing on trying to understand this one case, you know, try and prove as much as we can with the tools we have and sort of developing that. So it's very narrow at the moment, but I think that it can be extended to other situations.
Have you looked at all at K3 surface, embeddings into K3 surface?
Well, I think embeddings into K3 surfaces are not very interesting. It's certainly embedding into tori. There's a very general result by Entov and some algebraic geometry name begins with V, whose name is escaping me, showing that there are no obstructions when you embed into tori, because all obstructions basically, you know, one way of saying come from J-holomorphic curves, and there are no interesting curves in I mean, genus zero curves, no sort of persistent curves in tori. So for abelian varieties and things, there are no obstructions. Now, I would imagine that the same would be true for K3 surfaces, but nobody has proven it, or surfaces of general type. I think this is a phenomenon more for embedding into rational rules, rational surfaces. And even for ruled surfaces, you know, if you looked at S2 times T2, I don't think you'd see this. I mean, I don't know. So I think it may be just rational things that you get this structure. And in higher dimensions, as I say, if you just look at the simple problem, nobody has a clue. But if you look at what's called the stabilized embedding conjecture, so you look at domains which are compact four-dimensional domains, say times R2, and you look at when that kind of thing embeds. So you stabilize by multiplying by a Euclidean space. Then actually a lot of this structure persists. And I think the staircases persist, though nobody's actually checked all the details. So I think I should say, certainly the Fibonacci staircase persists under that stabilization. It's very robust. But that question is not, because the descending staircases that we found, which are the first descending staircases people found, to say that extends rather contradicts the intuition, that stabilizes rather contradicts the intuition I have about stabilized embedding. So something's going on that needs thinking about that I hadn't done.
Very good. Any questions or comments? Okay. So, well, let's thank Dusa again, and thank you very much for a beautiful talk.
Okay, you're welcome. It was a pleasure to give it. Yeah. Nice to see you all.
Well, thank you, everyone. So I'll see you in 1 week. We'll meet again.
Okay.
Take care.